So today we're going to be talking about the effects of other atoms on proton acidity. So in general, like I mentioned before, we're going to be talking about how do we know whether one molecule might be more acidic than the other without knowing its pKa. And so in general, the big takeaway is that the more stable a conjugate base is, the more acidic the initial acid is, right? The lower pKa it'll have. So I'm going to go over some general rules about that that'll help us determine the strength of an acid. So when we're looking at the electronegativity of an acid, as you proceed from left to right across the row and periodic table, the more electronegative the atom will be which the acidic proton is attached to, right? Making the bond between them more polar, and the more acidic the proton will be, right? That hydrogen is having electrons pulled away from it, making it more partially positive, right? So just looking through these examples here, where we know that the carbon-hydrogen bond is not really much different in electronegativity, like we've talked about. With nitrogen, it's a little more. Right, it's a little more electronegative, and so on. Right, with water, we know that's a pretty electronegative atom on oxygen, and so we know that we'll have the electrons pulled away from the hydrogen with more efficiency. Right, that bond between the hydrogen and oxygen will become weaker. Right, that hydrogen can be more easily taken away from the rest of the molecule, right? So the easier that acid, right, the easier that proton can be pulled away, the more acidic the molecule is, right? And this also kind of plays a role into resonance, right? We know that electronegative atoms are more happy with negative charges than less electronegative atoms, right? So that conjugate base will be more quote unquote stable, right? So an OH minus anion will be better than an NH2 anion, right? This will be more stable, quote unquote, right? Because of that more electronegative atom holding that more electronegative charge. So the second feature, right, the increasing size of A as we proceed down a column in the periodic table will mean that that acid is stronger, right? The acid strengths of the hydrogen halides increase in order of size. So the larger the atom, the longer the bond, and the easier the proton is removed, right? So we know from our periodic trends that fluorine is a pretty small atom, right? So if we were to look at the conjugate base of all these, we know fluorine is a pretty small atom, right? And if you go all the way up to iodine, right, I minus, right, it's a much bigger atom, way more electron shells that got filled. So we can say this is a much bigger electron cloud at the end. Right, so this is a much more stable molecule because the negative charge can be spread across that sphere a lot easier than the fluoride minus anion. Right, that's a much smaller, harsher conjugate base. Okay, so you can think about it that way, right? The conjugate base of these acids, right, with a larger atom, that negative charge can be spread across that atom more easily. Okay, making the initial acid much stronger, right? Because the hydrogen can more easily get removed due to the stability of the conjugate base, but also, right, because this is such a large atom, that hydrogen that is initially attached to is spread across a longer bond, right, because of, again, that size of that initial halide. And so another role that plays into effect here is resonance, right? So the resonance in the conjugate base, right, the A minus, that allows the localization over a charge of several atoms. So this effect is frequently enhanced by the presence of additional electron-negative atoms in A minus, right? So taking a look at these two right here, okay, let's look at ethanol right over here. Let's look at the conjugate base of that. Right, so let's just say, B minus takes away this hydrogen, this, and now we have O minus. There's no chance of resonance here, right? There's no resonance that can take place. So looking over at this molecule here, right, the only difference really between them is this oxygen that's double bonded to this sp2 carbon right here, right? That's the only difference between these two molecules, right? There's nothing else going on. So likewise, if we were to take a Lewis base, the resulting anion would be this. Now we see that there is a chance of resonance, right, with that sp2 carbon right next to it. So what we can do is do out a resonance form like this, right? So we're showing again the electrons being pushed in between the carbon and the oxygen, and then likewise the electrons here have to be pushed onto the oxygen. So we're making sure not to violate the octet rule on that carbon. And so now we have the negative charge spread across two oxygens instead of just one, right? Because with the resonance hybrid, we would say that that double bond is sort of spread across those two oxygens as well as the negative charge, right? So the final structure can have that negative charge delocalized across two oxygens, right? Making that conjugate base more stable than just the anion of ethanol, where the negative charge is just on the oxygen, has nowhere to go, so it is a much weaker conjugate base, meaning from the initial acid, this compound right here, right, this carboxylic acid, is going to be much more acidic because the conjugate base will be much more stable, right? And that's why ethanol has a higher pKa rate of around 15. And the same thing for water, right? It's also pretty close to 15, 16, because it has to go through kind of the same hoops, right? Because water doesn't have anywhere to go, or the negative charge has nowhere to go after water gets deprotonated, right? You just have this hydroxide ion, and there's nowhere for that negative charge to go, right? That's why water is also basically around the same pKa. And so similarly with this next example, right, we have a carboxylic acid again, and then we have this one with 3 chlorines attached to this atom, or to this carbon atom, right, over to the left here. And we know that chlorines, of course, are much more electronegative than carbon, right? And we see that's playing some sort of role with the pKa, where it's making this essentially a strong acid, right? It's very close to 0. So what's happening is that nearby dipoles in a molecule can affect the acidity of a proton, and this is called the inductive effect, right? So if we were to take the conjugate base of these, right, we see this, and then we also have this as a conjugate base. We see that there's resonance, right, in the case of each of these, right, this negative charge can be delocalized between these two oxygens. So what else is happening, right? Why are the electronegative atoms taking such a big role? So if we look over here to this left one, right, this plain carboxylic acid, right, with no chlorines on it, we see that there's not really any dipole moments happening over here, right? There's no electronegative pull that's happening that can pull away the electrons from this delocalized negative charge. But over here, right, we know that halogens are much more electronegative than carbons, right? So we have this partial negative pull happening that's pulling away the electron density from the carbon, making it very electron positive, right? So overall, this sort of negative charge cloud around the two oxygens are being pulled towards the chlorines, right? So they're sort of artificially pulling the negative charge away from the oxygens and more towards themselves, right? They're sort of helping to spread that negative charge around, right? If we were to sort of think of it just like a sphere, right? So it's like this is where we have our negative charge. Over here, the negative charge, you could say, is spread out more evenly, right, across the entire molecule, right? There's a more expansive spread of that negative charge, right? Maybe we can also draw it in here so it makes a little bit more sense, right? And that carbon down here isn't really doing anything to help spread the negative charge, so it's mostly localized across those two oxygens, but over here, the whole thing is sort of contributing, right? These three chlorines are helping to spread that charge around. Right, not as much as resonance. You see, it's not like, it's not a huge difference, right? But it is helping to spread that negative charge a little bit, right? I hope that makes sense, right? So in general, these electronegative atoms are going to help spread that negative charge from the resulting conjugate base across the entire molecule, right? More so than just these three hydrogens are doing, right? They're effectively doing nothing to help spread that negative charge and making the conjugate base more stable in the end. So another example of how we can sort of tell if a molecule is more acidic based on its conjugate base is through hydrogen bonding, right? So remember, hydrogen bond is essentially a much stronger dipole-dipole interaction, right? So hydrogen bond is formed between a partial positive hydrogen and a electronegative atom, right? So if we get a hydrogen bond formed in the conjugate base's anion in the same molecule, the original acid becomes more acidic because the resulting anion is stabilized through this hydrogen bond, right? So if we look at these three molecules here, you see that they're very similar, right? The only difference is the placement of this OH group, right? This hydroxy group, right? So in this case, it's right next to this acid group, right? We move it over here, it's one carbon away. We move it over here, it's now 2 carbons away, right? So if we were to draw out the conjugate base for each of these, we would see that the hydrogen bond resulting from the conjugate base is being moved further and further away. So I'm going to draw the conjugate base of this molecule, right? We say it takes this one, there's no bond here. I'm going to draw like a little tiny one in there just so you can see kind of what's going on. Right? So the resulting molecule will look like this. I'm drawing out that hydrogen on the oxygen here for some clarity in a second. Right, and so we can see now that that hydrogen, right, is right next to this oxygen, right? And remember from dipole moments, of course, that hydrogen on that OH group up here is going to be very partially positive, and the oxygen will be very partially negative, right? And of course, this is straight up negative, so we know that there is this hydrogen bonding interaction going on between them, right? We have H bonding. And what that's doing, similar to the last example with inductive effects, is it's helping to spread that negative charge, right? We have this bond forming right here, right? That this hydrogen bonding happening right here, right? This intramolecular force that is going to be helping stabilize the conjugate base, right? Because of this interaction, right? So, and in general, this rule can apply to any stabilizing intramolecular force happening to determine the acidic strength, right? So if we were to draw out the conjugate base of these two, and I encourage you to do this on your own just so you can see, that OH is going to get further and further away from the resulting oxygen anion that is forming that hydrogen bond, right? We see, it's not a huge difference in pKa, but there is definitely a difference, right? With this, right, with the lower pKa being the most acidic, right, it has the most hydrogen bonding going on, up to this one where the OH is the furthest away from this acid group, and it has the least hydrogen bonding stabilizing effect going on, so this is the weakest acid of these three, okay? And so the last effect I want to talk about is with hybridized orbitals, okay? And so you notice between these, right, they're all, same number of carbons, where you have 2 carbons, but the only difference between them is the hybridized character, right? So this first one, right, it's just sp3 carbons, second one, just sp2 carbons, and the final one is just sp carbons, right? And so what's happening here is that the more p character that a conjugate base has, right, that means the lone pair is going to be further away from the nucleus, and it's going to be more reactive, right? It's going to be more acidic, okay? That initial acid is going to be more acidic. And you can kind of think about it like this, right? So if we were to draw the conjugate base of, right, this sp3 carbon here, okay? Right, this is what it looks like, okay? And we know from our hybridized orbitals, right, that with the more hybridized orbitals you have, the more p character that orbital is going to have, okay? And so if you remember, right, s orbitals look like this, and p orbitals look like this, okay? So with an sp3 orbital, there are two more p orbitals that are contained in the sp3 orbital, right? So px, py, and pz, or interchanged however you like, okay? So when you combine them to get your hybrid orbital, right, it's going to have more p character, right? That those electrons are going to be more extended in general, okay? So your final sp3 orbital will look kind of like this, okay? And conversely, if we're going to look at, you know, of course we have phases in here, so get those in if you like. If we're going to look at the final example here, right, this alkyne, right, this triple bonded example, right, the sp hybridized orbital just has one p orbital and one s orbital taking place, right? So there's more s character in the final results, okay? And so you can sort of see by my drawing example here that with the sp orbital, right, has way more s character, those electrons are closer to the carbon, right? But with the first example, right, the sp3 orbitals, right, those electrons can be extended further away from the nucleus, okay? And so what that means is that this is going to be much less, right, much less reactive, right, much less acidic. In this example here with the triple bond, this is going to be much more acidic, right? And so the further away the lone pairs are, essentially, or the further away the p character is from the carbon, essentially means the less acidic it is, okay? And it's sort of, you know, complicated to think about the orbitals in this fashion, where those lone pair of electrons lie. But do your best to sort of just kind of remember it generally like this, okay? sp3 orbitals are less acidic than sp2 orbitals, and sp orbitals are more acidic than sp2 orbitals, okay? Just think about it sort of like this in terms of acidic strength. Don't worry too much about, you know, the why, if it's confusing. So let's go ahead and cover these examples in lecture, okay? So what I want you to do, think about it a little bit first on your own, is what is the reason behind the pKa difference between the following molecules, okay? So why is this molecule here, right, with the 3 fluorines more acidic than this one with the 3 chlorines? And why is this example here with the oxygen, right, on H2O, why is this less acidic than H2 sulfur, right, H2 sulfide? Why is this molecule more acidic than this one?